Good morning, my name is David Chm151 and I'm here to do a tutorial video about reactions and balancing. First reaction we're going to be looking at is synthesis reactions, a reaction in which two or more substances are combined into one. Typically, a synthesis reaction can be identified by there only being one product. The glorious example here, of course, is NaCl, in which sodium combines with carbon, or binds to carbon, forming sodium chloride, table salt. Next up is the decomposition reaction, in which a reaction in which a reactant breaks apart into multiple products. A decomposition reaction is usually identified by there only being one reactant. This wonderful example here is germanium and oxygen breaking apart into germanium and oxygen. Oxygen normally pairs by itself, thus it is left as just O2. Next up in the reaction list is single replacements. Single replacement is a reaction in which a compound has a part of it replaced by another reactant. Easily identified on how a reactant compound has a part of it replaced and swapped out for another reactant. Example here, of course, is sodium nitrite and chlorine swapping out with the nitrite, giving us, of course, table salt and nitrite, where the single replacement is sodium and the nitrite. Double replacement is a reaction in which two compounds have a part that is cations and anions swapped. Identifiable by how the compounds swap components, simple as. Where the components of these two, of course, is silver nitrite and sodium chloride, where they swap, of course, their cations or anions, whichever way you want to look at it, where the silver and the nitrogen, or not the nitrogen, the sodium, my apologies, and the chlorine and the nitrite swap places, as shown over here with the end product over here. Next up, of course, is a neutralization reaction. A neutralization reaction is a reaction when an acidic compound is neutralized by a basic compound, usually identified if the reactants have acidic or basic parts, or are acids or bases themselves. And the products include a salt and a water. And a salt is, of course, a compound that contains a basic cation and an acidic anion, thus balancing themselves out. Of course, the example here is hydrochloric acid, which is HCl, and potassium hydroxide. The hydrochloric acid, of course, is an acid itself, and the potassium hydroxide contains a base which can, through a double replacement, form a salt, which is the potassium chloride, and a water, or H2O. Well, look at that. Of course, next is the combustion reactions. In a reaction in which a reactant is combined with oxygen, and most products contain oxygen, and which releases energy into the environment. Here we have the wonderful reaction of C3H8 combining with 5 oxygen pairs, usually heated, thus the word combustion, giving us, of course, 3 CO2s and 4 H2Os. And that was your wonderful first look as we get into balancing. Balancing, of course, is when we get into how a reaction actually balances out with how many of what are we dealing with, and their charges. For instance, the very first one up here, the example of H2 plus O2 equals H2O. Well, that's simple. They should add together, except for that we have two oxygens, 2 hydrogens. But we have one oxygen on this side. So technically this is H2O1. So we need to balance this out, because we would need to only start with one oxygen pair, which would give us 2 of these, and to balance this out, because we need 2 of these, which would become 4 of these, we need 2 more of the hydrogens. Thus we need 2 hydrogens, or 2 hydrogen pairs, thus balanced, as 2 of these or 2 of the 2 of these make 4 hydrogens, 2 of these give us 2 oxygens, and the H2Os, since there's 2 of them, we need 4 hydrogens and 2 oxygens, which balances out quite nicely. And usually the products like to go off of charge, which we will show off in the next one with a single replacement. So copper has a charge of +2, and silver has a positive charge of +1, and nitrite has a negative charge of 1. Thus, when they exchange, we get copper NO3, or copper nitrite 2. So that way there's 2 nitrites with its -1 charge to balance out the +2 charge of copper. Thus, to balance this out, we only need 1 copper. We need 1 in the end. Thus, to balance this out, because there's 2 over here, we do need 2 silver nitrites, and we'll be ending out with 2 silvers right over there. Thus, all balanced out and all good to go. On to the next one, of course, is a double replacement between potassium iodide and sodium chloride, where the potassium and sodium swap places, giving us sodium iodide and potassium chloride. Thus, and since they're all -1 or +1 or +1 charge, we simply only need 1s in these places. For the how many of what do we need to form this reaction. Then there is titanium and oxygen. Titanium has a massive charge of +2. Oxygen naturally has a negative charge of, I believe, -2. My apologies. But to get this equal out, we need to equal this out so it nicely fits. So to get this to nicely fit, we need to make sure this balances out. So titanium, we need only 1 of this because it is the highest of charges, and we only have 1 of it in the end. Well, it seems like we only need the 1 for the end. And for the oxygens, we only need 1 pair, because that 1 pair should pair quite nicely with the +4 charge that it has. If we have 2 of these, we should have a -4 charge with the 2 of these, as oxygen by itself has a -2 charge. Thus, this equals out to 1, 1, and 1. Nice! Next up, of course, is a neutralization reaction, in which we have potassium and a potassium hydroxide and a hydrochloric acid, doing, of course, another double replacement to get into being a salt, potassium chloride, and H2O, and a water. So we need we need 2 H's in the end, 1 oxygen in the end, 1 chlorine, and 1 potassium. Because of that, we simply need to see where we're going to be pulling all these from, because the potassium hydroxide has 1 O, 1 H. That's going to give us one of the H's and one of the O's on this side. Our O, or our oxygen, for this area, for the H2O, and then the hydrochloric acid is going to give us the last oxygen we're going to need. And then for the potassium chloride, we only need 1 of each because they're both a +1 or -1 charge. Thus, we only need to put 1, 1, 1, and 1. Then, of course, the big one, C5, H12, and how many oxygens are we going to play this game with? As this is a combustion reaction, of course, equaling out to CO2 and H2O. So we do need to figure out how many of what do we need. Of course, we're only going to hopefully need 1, but if we need more, we can mark it up to 2 or higher, depending on how much is needed to equalize and balance it out. First up is, of course, CO2 and H2O, because we have 5 coppers, or not coppers, my apologies, 5 carbons, and we have a product that only contains 1 singular carbon in its structure. We only need, well, 5 of these to hopefully balance out the number of carbons we need. And for the hydrogens, we only need to half this number because the other product only contains pairs of hydrogens. So we can simply half this down to 6, and we find out how many we need. Now then, for the oxygens, we need to find out how many oxygen pairs we need from both sides. For every oxygen, for every carbon, we need a single oxygen pair, so that is 5 in total at base, but I'm not going to mark anything down yet, because we still need to find out how many we need from the H2Os. Because these come in oxygen pairs, due to Brinkoff particle rule, that oxygen likes to pair by itself, we know that we need to figure out how many oxygen pairs we need for H2O. Since there's 6 H2Os, we need to half this one more time to figure out how many we need to get down to 3. So we need 3 oxygen pairs to give us the total number of oxygens we need to satisfy this H2O. So that's 3 plus 5, that is 8 oxygen pairs we need. Thus solving the equation and calling it done with that. Now then, into a wonderful decomposition for last, which is going to be a calcium and a chlorine oxygen 3. And this is going to break up into calcium chloride or dichloride, and of course some oxygen pairs. Of course, we only need 1 of these because this is going to end out as 1. We already end up with 2 chlorides because of the 2, because it comes in as 2. Thus, this will give us so we just need to figure out how many oxygen pairs we have at the end of this. And of course, the last part is, well, how many do we have? We have 3 oxygen pairs in this group right here, or 3 oxygens in this group right here, multiplied by 2, because that's how many groups of this do we have. Given together, of course, we will have, well, 6 oxygens going in as reactants. Thus, the amount of oxygen removed is oxygen pairs removed is 3. And with that, I believe we are done, and this little tutorial video is coming to an end. Hope you learned something, and I hope you have fun.